Alright, this is going to be a little bit of a long discussion, but I want to make sure all the pieces are in place. So for instance, this is going to be one of our setups to find something about the weight of an object on a ramp. So generally, we'll be given this angle over here, let's call it theta. So this would be the angle of elevation of the ramp, or the grade of the ramp. And what I'm interested in is the weight of the ramp is going to be pulled down towards the center of the Earth by gravity, perpendicular to any horizontal line. So this line here would represent the weight of the object. So if the object is sitting here, this line is going to represent the force that this object is going to apply in a downward motion. And this line here, if the object was sitting here, would be the force of the object upon the ramp itself. So notice that it's going to be a little bit shorter than the weight of the object according to gravity. So some of the weight is going to want to go down the ramp, the rest of the weight is going to apply through the ramp. So what I'm interested in is this blue triangle. That has a lot to do with how an object relates to a ramp of an angle of elevation. So using properties of geometry, we're going to look at this two different ways. So I can call this beta, and I know something about theta and beta. Theta and beta have to add up to 90 degrees. They have to be complementary, because this angle here is a right angle. And all the angles of a triangle are 180. All right. So since this angle is beta, the one straight across it through these two intersecting lines is congruent under properties of geometry. So this is also beta down here. And this here is also a right triangle. So here we have beta in one corner. We have a right angle in the other corner. That forces this bottom angle way down here to also be theta, because theta plus beta have to add up to 90. That's our guarantee from our little triangle here. So this angle is theta, and so is this one way down here at the bottom. So that's one way of proving that theta here and theta here are exactly the same. If I drew the picture with this whole rectangle, then this angle up here is also theta, because this is a transversal. These two are parallel lines, and these two are called alternate interior angles. Alright, so now that I know what this angle is, I can describe this blue triangle in much more detail. I'll know the length of this hypotenuse, and I'll have this angle down here, theta, so I'm going to be able to find both sides of this right triangle. Alright, so that comes in kind of handy. So here I got some kind of mass on top of a ramp that has an angle of theta. And notice in this picture that I have theta here, and theta here. I like drawing the rectangle that goes through these forces. It kind of gives you a hint that all your forces, like this black line, can be represented by two other forces that add up to it. If you remember anything about vector addition, the vector addition, you can form a rectangle and draw the diagonal, and that becomes the sum of the other two angles. And this angle here, of course, is a right angle. So it's kind of a cool relationship that goes on here. All right, so let's say this has a certain weight of 200 pounds. Now, pounds is nice because that's a force. If we use kilograms, we'd have to mess around with some physics to change it into a force. So I'm going to try to stay with pounds so we don't have to do any conversions. All right, so this 200 pounds is being applied by gravity straight down. So this line, this vector, has a magnitude of 200 pounds. What I'm curious about is how much of the force is going into the ramp and how much of the force is being applied down the ramp. Like it wants to slide in that direction. So this would, if it was sitting still, this would be like a frictional force holding it up. All right, so let's give theta an angle. It really doesn't matter what it is. Let's say 20 degrees. So if theta is equal to 20 degrees, we should be able to find the weight going down the ramp and the weight going against the surface. So you can look at either triangle. It really doesn't matter, but I'm going to focus on this one. because that's my first theta, and this one I think represents the idea better because here's your force going down the ramp. That's much more important than the force against the ramp, unless you're trying to design a ramp to hold this force up. All right, so my curiosity is this side, so let's call it x. And while we're at it, let's just call this side y just to find it. So the relationship between theta, which is 20 degrees, this x, and the known number here is the side, which is 200. 200 pounds going straight down. So how do I set this up? Well, this angle has this as side as opposite, and this side is hypotenuse. So you'd go sine of 20 degrees is equal to opposite over hypotenuse, and solve for x. And this would be the weight of the object trying to go down the ramp. So you get 200 times sine of 20. Just make sure your calculator is in degree mode so that you can calculate this out. So 200 sine of 20. So the amount of the weight, the 200 pounds, that's going downhill or trying to go downhill is 68.4. So this would be 68.4 pounds of force are trying to go down the ramp. So to hold this object still, we would have to apply 68.4 pounds of force going in the other direction to keep it still. So if this was like a car, then the car would have to have brakes that could handle 68.4 pounds of pressure in the opposite direction. So if you have weak brakes, your car is eventually going to start rolling down the hill. All right, let's see how much is applied against the ramp itself. So that would be y. So here we have the angle. This side is adjacent. This side is hypotenuse. So that would be cosine of 20 degrees is equal to y over 200. And therefore, multiply by 200, cosine of 20 degrees, 187.9. So y is going to be approximately 187.9 pounds. So that's how you find out how much weight is going against like a driveway or an upward hill road where you parked your car. And then the force going downhill would be the other one. All right, so that's just the general setup of what happens when you put a weight on a ramp. Now we could extend this idea into a work problem. Now this part is kind of irrelevant for a work problem except for one thing. The amount of force going down and the amount of force going up have to be more in the going up. In other words, the magnitude of this vector has to be greater than the magnitude of that vector, otherwise the object would start going down. So if we apply this force pulling off angle a little bit, the object should go up the ramp. So that's going to create work. And work generally is force times distance, as long as the force and the distance are in the same direction. So if I had the force directly along this green line and I started pulling directly along that green line, then we could use this formula. The problem with this is the force is being applied off angle. So here we have a box is being moved up a ramp whose angle of elevation is 20 degrees. That would be theta. A force of 80 pounds is being applied at 15 degrees off of the ramp. Well, that's going to be alpha because it's 15 degrees off of the ramp. It's not off of the horizontal down here. How much work is done by moving the box 20 feet along this ramp? So like I said, even though the force is being applied in this direction, 80 pounds, we need to move the force in the direction that the motion is going, along the ramp. And the nice thing about this is it's a projection of the vector down onto this line, which has the same degreeage as the ramp. It's 20 degrees off the horizontal. So if I drew the horizontal here, this angle would be 20 degrees, this alpha would be 15 degrees, and the angle of elevation of that blue line would be the sum of those two, which would be 35 degrees. But for work purposes, this 20 degrees is irrelevant, as long as you know the angle off of the direction of the motion. Okay, So to do this, we're going to zoom up on this part of the picture. This is the one we're interested in. So let me move one more, and we got to zoom up. Oh, and I need to put my little line in there again. So drop the perpendicular. That creates a projection of the blue vector on top of the green direction. We get this nice little green vector. Now, that it's a vector is kind of irrelevant, but it comes handy in physics. So let's give this a little poundage. This thing is 80 pounds of force, so this side has a magnitude of 80 pounds of force. What I'm interested in is this side, how much force is being applied in the correct direction. And I know my alpha here is, where is it? 15 degrees. A force is being applied 15 degrees off of the ramp. So this is 15 degrees. And we have a nice little cosine setup here. Angle, adjacent, hypotenuse. So we can do cosine of 15 degrees is equal to x over 80. And therefore, x is equal to 80 cosine of 15. I like my parentheses. All right, so this is the amount of force in the right direction. So I'm just going to call it F1. This would be F, and this would be F1, the force that's really being applied. So then I just go to my formula, work equals force times distance. And in this case, the force is 80 cosine of 15 times the distance that we're going to move it, which is, oh, there it is, 25 feet. So times 25. So let's put this in our calculator. 80 times cosine of 15 degrees times 25. And we get 1931.9. Now the measurement here is a little odd. Cosine of 15 degrees doesn't add any measurements. Force here was pounds. Distance here was foot or feet. So this gets called a foot-pound. It's a strange measurement. It works better if you deal with kilograms and meters and all that fun stuff. But for our purposes, this is the work done to move this object 25 feet up that ramp. Okay, one thing to notice here is this formula looks kind of familiar. So if we have work equals force times distance times the angle separating those two, oops, I don't want to call it theta, let's call it alpha. The angle separating those two, so this is the distance you're traveling, this is the angle of the force, this is the angle that separates them. This should look quite familiar to you if we start putting, vector notation in here. Force is a magnitude, distance is a magnitude, so this is the magnitude of the force vector, the magnitude of the direction vector times cosine of the angle that separates them. That's the same thing as the dot product between their vectors. It's just a neat little observation. Now here force is a magnitude. Here I'm representing this vector f. So that would be the component vector of f going in that direction. Oh, I'm sorry. The component vector of f going in this direction, whatever its magnitude and direction is. And the distance would be this magnitude 25 feet long going in this direction. So there is a little correlation between dot product of vectors and work. You'll find that out in calculus.